Okay, we're recording. So this is called Chapter 3, the normal distributions. It's actually a different chapter in the electronic textbook, and we'll open that up in just a little bit so you can see how that looks. But let's have a little discussion here about what we see. So this right here is called a density curve. If we read some of the bullet points about it, it's an idealized description that we use because they are easy to use and accurate enough for practical use. The word used is done often there. Always on or above the horizontal axis, okay. Have an area of exactly 1 underneath the curve. So we think of the curve as being 100%, or sorry, the area beneath the curve as being 100%. Yeah, area in the curve and above any range has a portion of all objects that fall in that range. Comes in many shapes. So let me just talk about this right here. So sometimes we'll see a curve that looks like this. And usually maybe we're interested in maybe half of the curve. Sometimes we might be interested in 75% of the curve or whatever. But we are going to heavily look at the proportion. And that's going to represent how many data points we're looking at. Now, the median. The median of a density curve, so this again is called a density curve. And in some ways, it's kind of like a histogram. For example, let's say you're looking at the vocabulary score on a quiz, and let's say it's a 12-question quiz, and you're curious like what people's scores were, or a 12-point quiz, we'll say that. You can see a whole bunch of people maybe scored like maybe between a 5.75 and a 6. Or some people scored like between an 8 and an 8.25 or something like that. So essentially what you're doing is you're taking a histogram and kind of drawing a curve through the top of each of the rectangles. The median obviously will be the point that divides the area under a curve in half. Now, obviously we have a very nice symmetric curve here. This is very nice and symmetric. That's not always true. You could see something like that that's a bit skewed. But your middle, you still want to kind of figure out what the middle would be. Maybe the middle would be like right here. Just depends on how the curve is designed. But the median will always be right where it cuts the area in half. 1/4 of the areas we'll call Q1. 3/4 we call Q3. And anything between Q and Q3, remember, we call it IQR. Now, if it's symmetric, the median is right at the center of the curve. Like in this case, we could probably say my median is right at the center. Now, the mean is kind of like a balance point. Is at which a curve would balance if made of solid material. If you actually were to have something that were solid and take on this kind of like three-dimensional shape, that's where it would balance. Sometimes what happens is that when you're right skewed, like in this case here, we're right skewed, the mean is going to be greater than the median. And we actually had that on the test. We had a question about that. So what's happening is that you have some data points that pool the mean to the right. So a good example is we talked about in the past, like home prices in San Mateo County. Median home price probably around $1.52 million. Most homes in the Bay Area, or sorry, in San Mateo County, probably located in Redwood City, San Mateo, of course, Burlingame, Millbrae, Belmont, San Carlos. You have a handful of homes, let's say handful, but a smaller percentage of homes like in Atherton or Hillsborough. Those homes are obviously worth a lot of money. That would cause the mean home price in San Mateo County to be higher than the median because you have those outliers that are pulling it to the right. So that's just something to keep in mind. But if you do have something that's perfectly symmetrical, the mean and median do line up. So these are actually equal when you have a perfect symmetric curve. Like that right there. We'll keep moving. So density curve is an idealized description of distribution. Let's talk about how this distribution means how are the data points distributed, right? And so again, we use like a histogram here to kind of show like, okay, you know, like a certain number of people scored in this range, certain people scored in this range. So that's called a distribution. And a density curve helps us to visualize that distribution. That's what density curve does. Helps to visualize distribution of data points, of all your data points. Now, when we look at our actual observations and density curve values, some things that we have to keep in mind are the mean and standard deviation. And we actually use symbols to represent them. This I call X bar. Obviously, I have a bar on top of the X. This, you know, is just simply called an S. This is called sigma. And it's called mu. Actually, they're already written for you there. So this is what you get from what we call a sample. And this is what we get from our actual population. So obviously we're going into an election year. And maybe you want to get the mean of the voter's age. Obviously, you have to be at least 18 to vote. And so you could say, for example, you know, say look at San Mateo County. What is the mean voter age of San Mateo County? So mu would actually be, you know, if you actually were to survey everybody who votes in the 2020 election, that would be mu. That would be the population. But that might be hard to pull off, right? So if you just like sample maybe 1,000 people out of all people who voted in San Mateo County and then took their average, then, you know, that would be, you'd be using X bar. That'd be a sample. Normal distribution and curve. So we say, so when you have a normal distribution, so normal, right? What does normal mean? It means that the curve is symmetric, has one peak, and is bell-shaped. And it can be described data in many real-life situations. And so, you know, some things to keep in mind. It could be, you know, used for characteristics of biological populations. Like again, like if you're looking at like the age of a certain group of people, or maybe the income of a certain group of people, stuff like that. Just taking an exam, like test scores. Think it's like the SAT, for example. Repeated measurements of the same quantity. So you're measuring like the weights of like dogs. I don't know, that's kind of random, but you know, so you know, and then you want to kind of like see how those weights are distributed. Like maybe you're looking at like the weights of like golden retrievers that are 2 years old. You kind of, and you know, and vets, you know, veterinarians obviously they kind of know like what's a normal weight for your dog. So maybe it's not too random. I know, like I see Isabel's got a picture of her dog there, right? You know, so like yeah, as soon as you go to the vet, you want to make sure what is kind of expected. My daughter, for example, she's not a dog, obviously, she's a human being, but you know, she's 11 months old, and we take her to the doctor, and you know, there's actually a chart, you know, kind of a distribution that the pediatrician looks at to see, okay, like is my daughter, what, you know, is she kind of right in the middle with her weight range? Is she at the higher percentile? Is she kind of too low? Maybe we need to feed her more food. You know, and then likewise with height. And those are things that are measurements that are repeated, right? Like we, you know, you know, weigh kids over and over again to kind of see you have reliable data there. A normal distribution can be a good approximation to result in many kinds of chance outcomes. Provides the ability to make statistical inferences for other roughly symmetric distributions. So basically what this means is kind of help us make, in a way, predictions, like what we kind of expect to happen. And so knowing the mean and standard deviation allows us to make various conclusions about the normal distribution. So again, we use that Greek symbol called mu, call that Greek symbol called sigma. And again, we put it right in the middle, right in the middle. So for a normal distribution, because it's symmetric, the mean will equal the median. Very, very important. So the mean will be the 50th percentile in a normal distribution. Now, another thing that's important to look at too, and this is a part that I think is really, really kind of neat and really kind of cool. So it's called the 68, 95, 99.7 rule. So if, and this is only true for normal distribution. So 68% of your data, so this is going to be the median right here, or mean. 68% of the data fall within one standard deviation of the mean. 95% should fall within 2 standard deviations of the mean. 99.7 should fall within 3 standard deviations of the mean. So let me kind of explain that in a little more detail. And let's actually do a more tangible example. And as I said, the baseball postseason is starting, and I'm a big sports fan. So let's look at home runs. Hit during the 2020 season. So baseball had about 60 games or so, a little less than usually they play 162 games. I think 162 games probably provides more reliable data than 60 games because maybe a team just gets really hot for 2 months and then they cool down. But let's investigate that. And let's calculate the mean. Let's also calculate the standard deviation. And let's see where the data lies. So what I'm going to do is I'm going to go to Google Chrome. I'm going to go to ESPN. I'm also going to share a new spreadsheet with you guys. So create and share. We'll call this, and I see there's a question in the chat, just give me 1 second. So September, okay. For some reason, Google does not want to respond. September 29 plus then, statistics. And let me share it with everybody in this room. I think that should cover everybody. Great. And everyone is has editor privileges. Okay. So let's look at the data first. This is NBA. Let's go to baseball, MLB. Let's go to stats. Okay, it looks like the A's are playing right now. They're now down 3-0. So if you're an A's fan, sorry. They just have bad luck in the postseason, unlike the Giants. Personally, I have a soft spot for the A's. I grew up in the East Bay, but Giants first. They saw each other in the World Series, gosh, 31 years ago, 1989. I was in 7th grade, I think. And I was really sad because the Giants lost to the A's, so that's why I'm a Giants fan first. Even though, again, I have a soft spot for the A's, I do not dislike them. Okay, Anyway, so let me copy and paste that over. Geez, let's try it again. Paste values. Okay, that's being silly. Let's try that again. That might be okay for us. Don't know why it's doing that. Let me try this one more time. Why is it doing that? I might have to transpose. No. Let me try this again, guys. Hold on. Let me try this in a normal spreadsheet. It might be better. I'm going to move it over to Google Spreadsheet. So this Google Spreadsheets has some issues. Just wait here for a sec. Okay, let's try that again. Okay, yeah, that's totally, and I don't care what team is associated with this. I just want the data here. Okay, so these are the home runs. I'm just gonna put this now in the Google Spreadsheet. Yeah, Google Spreadsheet just has some weirdness to it. So home runs. There we go. Okay. So these are home runs for 30 baseball teams. You can see we started cell A2 down to cell A31. And this is home runs 2020 MLB regular season. Actually, let me do that. You could, yeah, I'm a little OCD when it comes to this kind of stuff here. Formatting, let's Control X, do that. Okay, so now what we're gonna do is we're gonna calculate the mean, and standard deviation. So here I want the average, just do average of A4, then we to A33. So the average number of home runs hit by Major League Baseball teams during the 2020 regular season was 76.8. Apparently this team did really well, hit 118. Who was that? I don't know, I closed it down. So look at this one. Looks like it's probably Chicago White Sox. I don't know. Who was number 11? Oh, LA Dodgers. Yeah, they're really good. White Sox are good too. The Rays have been hitting the ball well. Anyway, standard deviation. So now I'm going to do equals stand div, and we'll do this the population because this is the entire group we're looking at from A4 to A33 again. So you have 15.546. Okay. So going back to the worksheet, let's assume that this is for home runs for Major League Baseball. So the mean again that we got was, my memory sucks these days, 76.8 and 15.55. So 76.8, 15.55. So 76.8. And the standard deviation is 15.55. So what a normal distribution is telling us is that 68% of my data, the number of home runs hit, is going to be between 76 point, that's supposed to 76.8. Yikes, sorry about that. 76.8. So it's going to be between 76.8 minus 15.55 and 76.8 plus 15.55. So if I get a calculator out, 76.8 plus 15.55, 76.8 minus 15.55. So it's between 61. So this right here would be 61.25 home runs, and this right here would be 92.35 home runs. So we expect 60, if our data follows normal distribution, if the number of home runs hit follows normal distribution, we expect about 68% of the baseball teams have hit home runs between 61.25 and 92.35. Let's take a look. Let's go back to our spreadsheet. We go back to our spreadsheet here. Let me actually sort this in order. So you go to data, sort. So you sort it. And again, one standard deviation below, one standard deviation above. Again, I'm doing that equals D4 minus D5 and equals D4 plus D5. Okay. So what data points would fit in that range? Obviously, all these data points here. So it looks like there are a total of from 10 to 28. So from cell A10 to cell A28, that's going to be a total of 19 baseball teams. 19 MLB, Major League Baseball teams, fit in that range. Now, there are 30 baseball teams. $19 divided by 30. Close enough. It's not spot on, but it's close enough. So about, close to 2/3, 0.6333. If we had 20 out of 30, it'd be a little more impressive. But hey, we're off by one baseball team. 21 out of 30 would been 70%, right? Then you're a little over. So we're, no pun intended, we're in the ballpark, right? We're close enough. I love baseball analogies. They're always fun to do. So anyway, that's good. Come on. Now, to be within 2 standard deviation would be 95% of teams. So what if I then multiply these by 2? So let me erase this. If I want to be within 2 standard deviations, right, it's going to be this times 2 and this times 2. Well, let's work that out. Let's see here, times 2, and make that plus. So now, let me erase all the stuff down here. So when you're within 2 standard deviations in a normal distribution, it's more inclusive, right? It's adding 95% of the data. Oh, and actually, hold on. I know there's a question in the chat. Let me get to that. No worries. Okay. So, 45.7. And 107.9. So we expect 95% of baseball teams to have hit home runs in between those 2 numbers. Let's go look at our spreadsheet again. Oh, the Google spreadsheet, here we go. So again, 45.7, 107.9. So that's almost all baseball teams. Obviously, there's one that did not, the LA Dodgers. They're a really good baseball team. So that would make them, of course, an outlier. 29 out of 30, that's 96.7. So we see that there's a lot of reliability with this distribution stuff. So 20 out of 30 obviously had within 2 standard deviations, which was 96.7%. So it's always kind of interesting when you look at this stuff. In colleges, for those who are seniors, that's something that they will look at too. They'll look at like, hey, we have like, a typical GPA that we admit. This is the mean GPA of the students we admit to this college over the last like 10 years. And maybe we have like 2 or 1 standard deviation. I know we can't really use SAT scores. A lot of schools have gone test optional, but that's something they've used before as well. So it's a very heavily used distribution. And you kind of assume that when you have a lot of numbers, even though I only have 30 baseball teams, they have played 60 games. That's a significant number of games they played. So we can kind of assume that as the numbers get bigger, that we tend to get closer and closer to a normal distribution. That's the other thing that's really kind of cool about this stuff. So let's keep moving here. Any questions so far? And if you have any, you can speak in your microphone or put some in the private chat. Okay. So now let's start applying this rule to nothing that's as exciting, but then we're going to talk about a z-score in just a little bit. And then I'll give you guys a little break so you guys can do some practice. So we'll go ahead and clear this here. Okay. So example in men's heights. So when you see something like this here, this represents the mean, and this represents the standard deviation. So we apply the 68.9599.7 rule. So 68% of our data will be 70 plus or minus 2.8. And you can control as plus or minus to make it more concise. So 72, so basically a man's height. So what this means, so I put 68% here. This means that 68% of men are between, what is that, 67.2 and 72.8 inches tall. So that's what that would indicate to us. Then 95% of our data will be 70 plus or minus 2.8 times 2. So 95% of our data are within 2 standard deviations of the mean. And then 99.7% of our data will be within 3 standard deviations of the mean. So a lot of our data is going to be, almost all our data pretty much will be there. Plus or minus 2.8 times 3. Now let's look at part B. What proportion of men are less than 72.8 inches tall? Well, if you have your distribution like this, your median is right at 70, or your mean, same thing for normal distribution. That actually can be interchangeable when you talk about normal distribution. And 72.8 is right here. So 50% of my data is right here. That's a little hard to read. Let's do that. 50% would be right here. And this would be actually, hold on a sec. About 34% of my data will be right there. So to be in between 2 standard deviations, let's go back up again a little bit. 68% is within one standard deviation, right? But this question B is asking something a little different. How many people are less than 72.8? So you don't want it to be between these two numbers. You want to be less than 72.8. So in this case, it's going to be the 34% between the mean and 72.8, and everything else to the left of the mean, which is of course 50%. So in this case, the answer is going to be 84% of my data. 84% of men are less than 72.8 inches tall. Question in the chat. Oh, great question. Yeah, how do I calculate 34%? No, I'll redo that in just a sec. If you take a look at this right here, Will, that's 68% of my data right here. So that right there is 34%. And that right there is 34%. And if this were 70 inches tall right here, that's 72.8, then I want all this data. So you have your 34, 34, and then you have this remaining part, which is going to be 16%. And this remaining part, which is also 16%. Or if you dissect it a little differently, so 95% of our data is within 2 standard deviations. So you can say this is 34%, 34%. We could say this right here is about 11. That's within 2 standard deviations. So that means that these are 2.5%. And those are 2.5%. Because to be within two standard deviations, you have to be in the middle of 95%. So the tails are 2.5% each, the right and left tails. And so then, what was that, 37.5? So this would be about 12.5% right here. Think. No, hold on. I should be able to do my math here. No, it's 13.5 like that. So we kind of dissect it in this manner. That's what we're getting. And we're going to be working this a lot over the next couple of weeks. So you're really going to be very familiar and comfortable with this data here, or that distribution. Now, there's a way you can actually compute that in the calculator. And here's how you can do it. So you may want to get a graphic calculator if you have it. I'm going to pull one line up over here. We'll go to TI Smart View. I think that's the one. Here we go. Let's take that sweet little time there. Okay, now next. Okay, 1 sec here. Okay. Let me clear that or quit. Okay, so what you're going to do is if you hit second distribute, I believe that's the right place to go. And I think if you do, let me just actually do it here first because I don't like to tell you guys when it's wrong and then like I'm so confused. So give me 1 sec here. Let's make sure I got this right. Well, let me try one more time. Okay, that worked fine. Give me 1 second. It's not quite what I was hoping it would say. One more sec, guys. I'm almost done here. Cool, got it. So what you want to do is pick option 2. Pick option 2. It's going to look like this. Now for lower, leave that alone. Don't touch it. Leave it as -1 E99. I'll explain what that means in a little bit. For upper, you're going to do 72.8. Your mean was 70, and your sigma was 2.8. Then you're going to hit paste. What the calculator is doing is calculating the area of the normal curve. So if I, come on. So if I have a curve like this, And again, here's 70, here's 72.8. It's giving me the percentage of all this that's covered. Everything to the left is 72.8. So that's what this lower and upper means. So 72.8, of course, is, you know, the upper part of my region. The lower, it's kind of like way out here somewhere. So you're kind of assuming going forever to like, sometimes you can have negative values depending on what you're kind of measuring. So that's why I said just leave that alone. And if you hit paste, we'll paste this into the screen here, and it'll calculate the proportion that's covered. That's 84%, or 0.8413. So, and it does a normal, it's called a normal cumulative density function. That's what it's called. So that's what it computes for us. So this can be pretty handy. Okay, well, let's keep moving. So now the standard normal distribution is a normal distribution with the mean is 0 and standard. So usually when you do the normal distribution, typically you want to say the mean is 0 and the standard deviation is 1. That's just kind of like the very standard normal distribution. And there's something called a z-score. That's very important. So if a variable x has any normal distribution with the mean mu and standard deviation, as you see here, then the following standardized variable has the following distribution. So we call this a z-score. X is going to be your data point. It's going to be a very specific data point. That's going to be your population mean. And that's going to be your population standard deviation. So z-score is basically a measure of how many standard deviations the original observation falls away from the mean and in which direction. So it could be, z-scores could be negative, just so you know. Positive z-scores indicate higher than the mean, negative z-scores lower than the mean. And the larger the absolute value of these z-scores, because z-scores can be positive or negative, the farther it is away from the mean. So z-scores can be a way to measure, again, how much you, how far you are from the mean, or how many standard deviations you are from the mean. So think of z-score as the number of standard deviations from the mean. Think of it as that. So, for example, going back to that baseball situation, you can see like the LA Dodgers, you know, they're at 118. They're more than 2 standard deviations above the mean. Because when we did that, I think it was like 108 or something, 107, I can't remember. That was 2 standard deviations above. So the z-score for LA Dodgers would be higher than 2. That one there. So that's what's happening there. And using a z-score combination with a standard normal table, or what we did in the calculator, we could do that, do this in the calculator. One can find the cumulative proportion of observations that lie below the x value in question. So let me show you a table right now. So this is what I put in Schoology. There's something called a z-score table, but again, your graphic calculator could do this for you more efficiently. You calculate how many standard deviations you are above the mean or below the mean. So it could also be negative. I don't know why there are the negative ones. So you calculate this, like, what if your z-score is like 1.2? Actually, I guess in this case, that's 1.02. Then that gives you the percentage of scores less than whatever that z-score is at. And again, to calculate, all you have to do is take your observation, x, minus your mean, and divide by the standard deviation. Let's look at the LA Dodgers example again. They had 118 homers this year. The mean number of homers was 76.8. And standard deviation is 15.55. if I calculate that, 118 minus 76.8 divided by 15.55, I get 2.65. That's my z-score. So it means the LA Dodgers were 2.65 standard deviations above the mean. So 2.65, so 2.61, 62, 63, 64, 65. So this means that they did better than 99, so 99.59% of data points are less than the Dodgers. Now, of course, that's kind of weird because we only have 30 baseball teams, and their 29 teams have fewer homers than them. 29 out of 30 is not 99.59, but that's what we would look at. Sometimes when you look at tests, like if you take the SAT or ACT and they give you like your percentile, we would say this is 99.59 percentile, meaning that your score will be better than 99.59% of the data points that are out there. So that's how they calculate it. Or if you took the PST last year and they kind of give you like maybe your percent, if you score like a 700 in math and you have like that's a 98 percentile, I mean, your score is better than 98% of students who took the test. So z-score can be very, very useful. Really helps to understand how your data compares to other data points. You can also do this in the calculator. If you have a z-score of 2.65, there's a way we can actually compute that. Or you could actually, what's another way? You can also, if you have the percentile, you can get the z-score from that, but that's another situation. But going back to our calculator again, let me clear that. Second, distribute. So if you so desire, you could, so normal CDF. So I have the z-score 2.65. I'll change this to 0. I'll change to 1 because that's for a standard normal curve. And you should get 0.9959. There we go. Now, what if you want to be within one standard deviation, so one above, one below? So second, bars, option 2. So now I'm going to change this to -1, and that to positive. So if I want to be in between two standard deviations, in between one standard deviation, we have 0.6826. So those are some pretty nice things you could do, because using a table is a bit old-fashioned. But I want to show it to you because that's what I did when I took stats many years ago. So let's go ahead and, yeah, and I kind of already showed you. It's all kind of mentioned over here. So kind of the last page of notes I kind of already did for you, but we could talk about that later because I want you guys to do a little practice very shortly. So let's look at this question here. Say your professor grades your exams using the normal curve, said your raw score % correct, she posts your z-score. What kind of z-score do you want to see? Well, obviously a very positive z-score. What kind of z-score make you upset? A very negative z-score make you upset, right? If you got the average grade, what score z-score? Then your z-score is 0, right? If that happens. So I think what we could do is let's do some practice, go break some breakout rooms. Maybe do it for about 10 to 15 minutes or so. We'll come back at the end and kind of discuss what you guys have found. So let me pull this up here. So unit lesson 1 unit lesson 2 lesson 1 practice questions. This again, stuff that we've already been talking about here. So like you look at number 5, for example. A normal distribution is a mu or mean of 30 and standard deviation of 5. Find the z-score when it's 25, when it's 42. Find the raw score is -2. Find the raw score is 1.3. So again, the formula is going to be this. Z equals x minus mu over sigma. And so you're just kind of computing all these. And the raw score is obviously x, the score that you're looking at. 6 kind of works the same way. And then 7 says you consider the following scores: a score of 40 from distribution of that, a score of 45 from distribution of that. How did 2 scores compare relative to their respective distributions? So kind of have you guys think about that one, might be good. Here's another one that's good to think about. Raul received a score of 80 on a history test for which the classroom knows that, plus knows that. You see a score of 75 on a body test for which is blah, blah, blah. On which test do you think he did better? So that might be a good one to think about. Which student scored above the mean? Which student scored on the mean? Scored below the mean? The mean score was 150, students 20. What was the final exam score for each student? We'll see if we have time to get to that. That might be best to say for homework, and there's a bunch of other ones we could do for homework. But what I'd like you guys to do is don't worry about 1, 2, 3, 4. We'll see 5, 6, 7, 8, 9. If you have time, get to 9. We'll check in at about 1:33, so about 10 minutes. So to access this, all you have to do, go to Schoology. It's right here. And click on Unit 2, Lesson Number 1, Practice Questions. Again, you guys are doing 5, 6, 7, 8, and if you have time, get to 9. In about 10 minutes, we'll come back from the breakout room. Talk about it. If you're stuck, call me over. I'll help you out. But again, the formula is in your notes. You remember the notes are right here. The formula is right there. And again, a lot of times just asking for the z-score or what x is, and then kind of making comparisons. So yeah, so I'll have you guys do that right now. And let me